everyone. My name is Yara Gbagbo, and I'm the moderator for this session. And our speaker is Adam Rumpf. He's from the Department of Applied Mathematics from Florida Polytechnic University in Lakeland, Florida, and he's presenting on an accessible approach to differential equations modeling without differential equation prerequisites. So just a reminder, this is like a 20-minute talk with 5 minutes Q&A at the end. And just keep your cameras on and if possible, and your mics muted. Thank you.
Hey, thank you to everyone for being here. So first of all, just a little bit about myself. My name is Adam Rumpf. I'm an instructor in the Applied Mathematics Department at Florida Polytechnic University, where I've worked since 2021. Mathematical modeling is very important to me, and it's a big part of my background, and it's kind of what initially got me into mathematics. The first really interesting math class that I took as an undergraduate was a math modeling class, because that was the first class that I took that really showed me how broad and varied of a field math is, and how many different kinds of things you can study if you go into math. And that's eventually why I ended up majoring in applied math. It's also what the topic of my undergraduate research and my graduate research were about. My undergraduate degree was about math modeling for life and social sciences, and then my graduate degree was about operations research and optimization models. So this is something that I try to bring into all of the classes that I teach to the extent that I can. I try to take what's called a modeling first approach whenever I can, which means that whenever bringing up a new mathematical topic, I try to start by talking about a real world problem and then figuring out how to model that using mathematics. And then we develop whatever mathematical results we need to get to the answers that we want for that real world problem, which helps to contextualize everything and it helps to explain to the students why we're bothering to cover the things that we do cover. Um, and I'm sure that anyone at this conference would agree that if you're going to talk about mathematical modeling, then it's definitely essential that you talk about ordinary differential equations at some point, because they are such an essential and a ubiquitous type of mathematical model that shows up in all kinds of different contexts for modeling all kinds of real-world systems. They provide the language that we use for describing things that change over time, which describes most things in the real world, and that's why differential equations show up in as many different settings as they do. But I would say that they also capture a lot of the spirit of what makes mathematical modeling fun and interesting, because it's relatively straightforward to develop them. If you want to describe something that's changing, like a population, for example, you think about all the things that cause it to increase, you think about all the things that cause it to decrease. Those all become the terms in your model, so it's relatively easy to construct a differential equation model. And then there are a lot of really rich mathematical things that you can do to answer questions about it. They also help to show off the sheer variety of different kinds of problems that you can study if you become an applied mathematician, because they're used in all kinds of different seemingly different areas in STEM. They obviously show up all the time in physics and engineering because you use them to describe any physical systems that move over time. They show up all the time in mathematical biology for developing ecological models and for modeling spreads of infectious diseases. They're also good to know about if you're interested in game design, because knowing a little bit about differential equations tells you a lot about how to program things to move around a space how you want them to. That being said, they're also a somewhat specialized topic, and depending on your major, you may or may not see a great amount of differential equations during your time in college. There are usually only some majors that require taking a differential equations course, and if you want to teach a math modeling course, that can potentially be a problem because not all of your potential students will necessarily be very familiar with differential equations. So what I'd like to talk about today is I'm going to tell you about Florida Poly's first ever dedicated mathematical modeling course, which had been in the planning process for a couple of years now. It's an upper level applied math elective class. Last summer, I got to plan the course with one of my colleagues, Dr. Shamak Das, in the applied math department, and then we piloted the course for the first time last fall when I was teaching it. In particular, I'd like to tell you about some of the design challenges that came up in trying to plan the course so that it would be open to as many people as possible, since some of the solutions that we came up with might be something that you can use in your own courses. I should also mention, I'm only going to be talking about the first half of the course, during which we covered dynamical systems, specifically differential equations and difference equations. The second half of the course, we went on to talk about other types of mathematical models, so things like regression and graph theory and optimization. I won't be talking about those, not today, at least. So in particular, what I'll be discussing is some of the things that we did while we were running the course, why we made the design decisions that we did, and then some of the things that we learned and might do differently next time. Hopefully, what I'm about to discuss would be useful to anyone who's trying to plan an accessible mathematical modeling course of their own, or if not a complete course, then at least a course that's going to include a significant modeling component, or if neither of those things, it may at least give you some ideas for different ways that you could approach some typical differential equations topics. So first of all, just to give you a little bit of background about this class and why we started offering it. Florida Poly is a very young school and a pretty small school, but one that is growing pretty quickly. It first opened in 2014 with just over 500 students. We currently have just over 1,900 students, and that's increasing rather rapidly. So as a result, we've been developing a lot of new courses to add to the catalog and to start offering in recent years. Florida Poly is also an all STEM school. All of the majors at this university are STEM majors. And of those majors, the applied math department is extremely small. It's an extremely small fraction of the student body that is actually officially an applied math major, and as a result of that, when we want to offer upper level math classes, we pretty much need to make them attractive to students from other majors who might be interested in taking them as part of the applied math certificate program, or soon that will be a minor program. In particular, by far the biggest major at our school is computer science. So if you can make your upper level math course attractive to computer science majors, then that's a bonus. We do, of course, offer a differential equations course. It does take a modeling first approach, and it follows the Semiode textbook, Differential Equations, a Toolbox for Modeling the World. What it focuses on, though, is a rather limited and focused part of the book. In our class, in our differential equations class, we mostly focus on single differential equations, not systems of differential equations. And a lot of the course time is spent talking about exact solution methods, it's everything up through Laplace transform, along with some MATLAB projects to talk about numerical solutions as well. So here's the basic problem that we were faced with in planning our math modeling course. The computer science major, who we would really like to recruit students from, does not require differential equations for their program, which means that most computer science students haven't taken it. So if we were to make DiffEq a prerequisite for our math modeling class, that would immediately close off the class to a large portion of our students. Moreover, even if we did make diffeq a prerequisite for our math modeling class, we would still want to make the classes different from each other, and we would still want it to be worthwhile for students who had taken differential equations to take our math modeling course as well. And that sort of implies that our math modeling class should cover differential equations, but in a very different way than what students would see in our diffeq class. So essentially, the design challenge was this. We wanted to come up with an upper level math elective course to teach mathematical modeling. It needed to cover differential equations in significant detail because they're an extremely important type of mathematical model, but it couldn't rely on differential equations as a prerequisite. And also, it needed to cover enough things about differential equations that students wouldn't have seen in a diffeq class, that it would still be new and interesting for those students as well. So, here are some of the design decisions that we ended up making as a result of that. Um, a lot of those problems are seemingly contradictory, but there is a relatively simple way that you can address all of them by taking on sort of a simple design philosophy. And Generally speaking, that is to not focus on exactly solving differential equations. There's a phrase that I kept using throughout the math modeling class for my students while I was teaching it, and that is that you do not need to solve a dynamical system to learn everything you need to know about it. And once you realize this, it opens up quite a lot of new possibilities for how you can cover difference equations and differential equations. So broadly speaking, in our math modeling course, rather than focusing on exactly solving differential equations, which is most of what students would be seeing in DVQ, we focused on methods for analyzing them that don't require solving them exactly. In particular, the main things that we focused on during our coverage was the model development process, and then qualitative analysis techniques, and then developing numerical solutions for differential equations. So I'll address all of those in a little bit more detail in just a moment. But as for some of the benefits of this approach, uh, it improves the accessibility of the course and opens it up to a much bigger potential audience. And at the same time, it also gives students who have had differential equations something new that they wouldn't have seen in that previous class. This is also a very practical way to approach differential equations because in the real world, when you actually develop a suitably realistic and complicated differential equation, almost always it's going to end up being something that is too complicated and messy for you to solve exactly. So the kinds of techniques I was just talking about, like qualitative analysis and numerical solutions, those are what you actually end up using in the real world most of the time when you use a lot of mathematical models. So these are also valuable things to expose students to. So first of all, model development process. Obviously, that's something that we focused on throughout the entire math modeling course, but in particular, we spent a lot of time really focusing on it during our first unit, which was about difference in differential equations. Usually, people describe this as a cyclical process, and basically, the way that you think about it is you start with a real-world problem. You figure out a way to represent that in an abstract way using mathematical objects like differential equations. You do math stuff to those math objects to get whatever results you need, and then you map those back onto the real world to see what they would imply about what kind of behavior you should expect. And then you compare that to your intuitions or to data, and if it's not a good match, then you go back and change some of what went into your model. So some of the particular things that that means focusing on much more than students would be used to is being very specific and precise and intentional about the assumptions that you're building into your model. That means taking an inventory of what details you're deciding to ignore, what details you're deciding to include, how you think they work, and then also being very intentional about coming up with what variables you want to keep track of, what parameters you want to build into your models, precisely describing what they mean in the real world, what their dimensions are, what their units are, and then also working with real world data. These are all things that students touch on in other classes, but that was a very big point of focus throughout our coverage of differential equations. Next up, we also focused a lot on qualitative analysis in lieu of talking about how to exactly solve a differential equation. There are a bunch of different elements to that, but broadly speaking, what I'm talking about is ways of figuring out how you should expect a system to behave without needing to solve it exactly. So near the beginning of our coverage, that involved a lot of graphical analysis techniques, so using phase lines and phase planes. If you have a differential equation, then even if you don't know what its solution is, what you do know is what the slope of the solution curve is at every point, and that can be enough information for you to figure out what a solution curve looks like and how you should expect it to behave in the long term. We also spent a lot of time going through equilibrium analysis techniques, and broadly speaking, that just means thinking about the long-term behavior of a model. If you're looking at a population model, for example, should you expect it to increase without bound? Will it decay to zero? Will it approach some limit? Will it start cycling around some point? These are all things that you can conclude using some techniques like linear stability analysis, which we talked about in our course. And then there's also sensitivity analysis, which broadly speaking just means asking yourself how the behavior of a model would change if you changed its input parameters slightly. There's a precise way that you can do this called bifurcation analysis, but there are some other things that you can do if all you have is a numerical solution, which is the last thing that we kind of did instead of talking about exactly solving differential equations. Um, Developing a mathematical model is extremely valuable and important because even if you don't possess the mathematical background that you need to exactly solve it or to go through the analysis techniques that I just talked about, just having a differential equation means that you can get a computer to use it for numerical simulations. And for a lot of applications, that might be enough to get a general idea of how you should expect a system to behave. And that alone might be enough for you to answer whatever your research questions were. The other big important design decision that we made going into the class was to decide to make linear algebra into its one and only prerequisite. There's a few reasons why we decided to do this, but one of the big ones is the fact that pretty much all of our majors, including computer science, require linear algebra, so that would open up our course to pretty much all of our majors. It also guarantees that they've been exposed to at least a couple of things that were important for our class, including MATLAB, because our linear algebra class requires that. And it also guarantees that they've had at least a little bit of exposure to differential equations, because to get into linear algebra, they need to complete Calc 2, and they see some differential equations in Calc 2. More importantly, having students who have had linear algebra unlocks a lot of useful techniques for going through the kinds of equilibrium analysis and model development processes that I was just mentioning. For example, while you're developing a model, you can go through something called dimensional analysis, which basically involves solving linear systems of equations to figure out what dimensions make sense for your model parameters. Having a linear algebra background makes that a lot easier for students. It also allows us to work with systems of equations rather than just single equations, which exposes students to some new things that they wouldn't have seen in DPQ. And it's also something necessary for using linear stability analysis, which is a formalized way of figuring out the behavior of your solution around an equilibrium solution. As a bonus, linear algebra was also a big help when we got to the second half of the course and we started talking about different types of mathematical models. In particular, we talked a lot about statistical regression and then optimization models, and linear algebra is necessary for talking about those as well. We made quite a lot of use of technology in this course as well. Rather than talking about a lot of by-hand solution techniques, we had students working a lot with things like interactive Desmos demos and using MATLAB for numerically solving differential equations. So that was part of some of our in-class lectures. We showed students how to do things like solving a differential equation using MATLAB. It was part of their homework assignments, and we also included a MATLAB component as a take-home part of most of their exams. There's one particular piece of technology that I'd like to point out just because I found it very useful, and I think you might as well if you're running a differential equations class. Um, I I got the idea to look for this from a previous Symbiode Expo talk where they were talking about an app called Slopes, which you can use for very quickly exploring differential equation slope fields and plotting solutions and playing around with the parameters. This is a browser-based uh, utility, which is very similar to slopes. You can type in any differential equation you want. You can click around to see what the solution curves look like, and it's also very fully featured. You can, for example, include parameters in your differential equation and then give yourself a slider bar to immediately see how that changes the slope field and how that changes the solution curves. So we had our students use this for a lot of in-class activities and uh, homework problems to quickly see how the behavior of a model changes when you change its inputs without necessarily needing to go into details about how the solution process works. So I'd like to end by just talking about a few lessons that we learned and a few things that we might change the next time we run this class. First of all, if you are going to run a math modeling course, I would recommend going out of your way to try starting with an application that is a little bit messy and hard to wrap your head around. The very first example that we talked about in our class, because it was the first one that our textbook talked about, was it was the growth of a yeast population, which leads to the exponential growth model. There are good reasons for using that as an example because it's simple and it's very easy to talk in a lot of precise detail about important parts of the modeling process, like how to develop your model assumptions and how to use data to fit model parameters. But ultimately, I think it's a little too simple and too familiar to most students because most of them have already seen it before, and if they already think they understand it, then that gets some students to immediately stop paying attention. We also had to take a little bit of time out of class to drill down on some of the differences between difference equations and differential equations. We started by talking about difference equations just because they're a little simpler and they don't require you to talk about calculus at all. But a lot of students who were already familiar with ODEs wanted to treat difference equations just like ODEs. So we had to talk a little bit about the fact that they are different models, they do have different assumptions, and they can give you different kinds of behaviors. A good example of this is thinking about the logistic growth model versus the discrete logistic map, which can show you very different qualitative behaviors. Here's a Desmos demo that I might show you in a moment, depending on time. Also, just very generally speaking, I would recommend trying to cover less material and trying to set aside more class time to talk about specific parts of the modeling process and to give students practice with actually developing and presenting their own models. It's an important experience to try to set aside classroom time for. So rather than just lecturing about new material every day, if we could have like every other Friday set aside for them to just get together and work on a model and talk about it with each other, I think that would be a positive change. So in conclusion, if you are going to teach any kind of model-centric course or any course that touches on differential equations, I think it's valuable to keep in mind this idea that you don't need to solve differential equations to learn everything you need to know about them. And because of that, it is very possible for you to talk about differential equations in a way that doesn't depend on too many prerequisites. If you focus on the modeling process and the idea of qualitative analysis and applying numerical solutions, if your students have linear algebra background, that's a big help, but it's certainly not necessary. These are things that you could potentially use in teaching any kind of differential equation class if you just want to find some ways of making some of the material more understandable or just going out of your way to show them some things that they wouldn't normally see. So that's all I have for today. In case you're interested in seeing any of the code that we used in my class or any of the links that I went through in this presentation, that's all available on the course's GitHub page. Um, so that's all I have for now. But thank you for being here, and I'll be here to answer questions in case you have any.